Good morning, distinguished guests, ladies and gentlemen. Welcome back to the third keynote speech session. And now it is time for the third keynote speech. And of course, we are currently broadcasting live through our official YouTube channel. And once again, my sincere appreciation to both online and offline participants. Now let's kick things off by introducing our keynote speaker. Introducing Professor Uros Seljak from UC Berkeley. He's the professor of astronomy and physics at University of California, Berkeley, and Lawrence Berkeley National Laboratory. He'll be talking about AI for physics, physics for AI. And ladies and gentlemen, please welcome him with a big round of applause.
All right, thank you. Thank you so much for having me here. So I thought I'll give two different stories today. First story is how AI can help physics, and second story will be how physics may help AI. So let me start first with the first story. I am a cosmologist, and so I'll give you an example of how AI can improve the analysis and various things that we would like to achieve in analyzing cosmological data. So let me first give you a little bit of an introduction to the standard model of cosmology as we like to talk about it. So here is the picture of, let's say, our universe, which we believe started with the Big Bang in the very early times, so roughly 13.7 billion years ago. It started very small and hot, and then it expanded. And initially, this expansion was relatively easy to describe because it was following linear theory. And so our first observation that we have from this very early universe is called cosmic background. And it's easy to describe in terms of the modeling. But then later, nonlinear gravity kicked in, started to form these very nonlinear structures, such as galaxies, voids, and clusters, and of course, even smaller structures such as stars, planets, and after all, us as well. So that's the model in terms of the evolution. Now, what is driving this is what the universe is made of. And we believe the universe is made of is made of something which we call dark energy today. About 1/4 is made of something we call dark matter today, and then about only 5% is made of what we are made of. And then there are also even smaller components such as neutrinos and so on. All right, so then what are the open questions? Excuse me. So we would like to address these open questions by taking more data. I'll talk about what kind of data we'll be taking. But let's first talk about the questions. For example, neutrinos, I mentioned neutrinos. We believe neutrinos have mass. We don't know how much mass it may have. And so that will be one thing we believe we can address with cosmology. What is the total amount of matter in the universe, for example, amount of dark matter? What is this dark energy that I mentioned earlier? What's its nature? Is it cosmological constant that Einstein talked about, or is it something else? What are the signatures of the initial conditions of the universe? We believe initial conditions of the universe were set up by the process called inflation. Can we prove it? Do we have any tensions in the data that maybe are pointing to some discrepancies in our standard model? These are all kind of the questions we are grappling with today. And so how do we, and finally, of course, there may be something still unknown that we have yet to discover. And that will, of course, would be very exciting. Okay, so fortunately, we live in a golden era of cosmology, as we like to say, because we have a lot of experiments that we are building. These are both experiments from the ground, telescopes and stuff like that, or from the space, satellites. We have several satellites. And they measure a lot of different things. And so here's basically a rough time scale of when these things have started or will start and how long they will operate and so on. But you can see already from this that these are billions of dollars investments that we are making into trying to understand better the universe that we live in. Roughly speaking, we divide these experiments into three types. One is an example where we are taking images, and typically these would be images in some optical light, for example. So that will be one example. And a very good example of this is this Vera Rubin observatory. Another type is where we take images, not only images, but we also take spectra of the galaxies. And that way we can determine three-dimensional position of the galaxy. That would be this example. And a third example is this cosmic microwave background isotopies that I already mentioned. Okay, so here I'll be talking about these kind of observations and how AI can help extract information from these kind of observations. All right, so what is our baseline? At the moment, our baseline is measuring correlations between the different observations that we have. For example, if we have cosmic microwave background isotopies, we will have a map like this, and we would be asking what are the correlations between different points. This would be, we'll phrase this as a correlation function. If we Fourier transform this, then we call this thing power spectrum. It's the same thing. All right, so this is our summary statistic, if you want, that we then use to address questions such as what is the nature of dark energy, what is the nature of dark matter, what are the initial conditions of the universe, and so on and so forth. All right, and so power spectrum, for example, from SIMBI would look something like this. Okay, this is all fine, and this actually is an optimal statistic if you have Gaussian initial conditions and if the evolution is linear, and that indeed we believe to be the case for the cosmic background isotopies, because I remember I told you this happened very early in the universe. Now, as we observe the data today, we get, images like this. This clearly is not a Gaussian random field. This one is Gaussian random field, this one is not. And this then begs the question, how do we extract information from these kind of images? And that question is what I'll be addressing today with AI. All right, so basically these big data sets and these very non-Gaussian distributed data require new approaches that can handle large data sets and that are optimal. And when I say optimal, I mean optimal in the sense of extracting the best possible, in the best possible way, these cosmological parameters that I mentioned. So we want to get full information content from the data. And so the question is, can we capitalize on the recent AI developments? And the answer is yes. Can we take them off? Can we take off-the-shelf methods? The answer is no. And the reason for that is that we have very large data sets, and we need to account for symmetries, for correlations, and things like that. All right, so before I show you, before I go into more detail about this, let me just tell you what are the desiderata that we would like to get from AI tools. One is we would like to make simulations of the images of the data in a very fast way. So we call this simulations. And this would be a generative task, okay? So basically think of it as a generative model, but for cosmology data. Second task that we would like to address is how to get the best possible inference from the data. The inference is you have some data, like we call it X, how do we get some cosmological parameters Y? And then the third task is, do we have a complete model? Are there some unknown unknowns that we're missing in the data? So this would be more in the direction of anomaly detection, right? Are there any anomalies that we can detect from the data? So I'll address all three of them in my talk. Okay, so let me show you a typical example of the data and a typical change of parameters, cosmological parameters. So here I'm changing two different cosmological parameters. One is the density of the dark matter here in this direction, and one is the amplitude of strength of fluctuations that then relates to a lot of these other parameters I mentioned. Okay, so what you see in this case is somehow, I mean, I'm not sure you see, right, but as we increase this parameter, decrease this parameter, the voids get larger. And as we go in this direction, you see that the structure gets more clumpy. But this is all on top of some very stochastic processes, right? Every map here is different from another map. So these are very stochastic data sets. So, and moreover, they're very high dimensional. We would, even if we pixelize the data, we would easily have tens or hundreds of millions of pixels that we need to analyze. So these are basically very stochastic, very high dimensional data sets. And so that is why we need to bring in some symmetries and some simplifications in order to analyze this data. All right, and that's what I'll focus on in the remaining of this discussion. Let me introduce you a data set as we actually take it. Okay, so imagine you have a telescope here. It's observing some galaxies in the distance. All right, these will be the galaxies. Now, as the light travels to the universe, so think of these rays here of light, they actually get distorted by the presence of the matter along the line of sight. And what is nice about this thing is they get distorted by the presence of the dark matter that we can't actually see, but we see through these effects. We call these effects weak lensing effect. These are gravitational lensing effects. So basically, dark matter deflects the light. And as a consequence, if we started, for example, with the galaxies that look like this, all the same, as they propagate through the universe, we would get them distorted. We'll get them, their shapes would be elliptical in different directions, depending on whether there's more or less dark matter along the line of sight. And from this kind of map, we can actually restore this map, which is the projected dark matter density along the line of sight. All right, and so this, you can think of this as a proxy for this, and this is what we would like then to relate to the underlying cosmological parameters. All right, so these, again, these are very highly non-Gaussian maps, but also highly stochastic maps, and so we want to use data-driven methods to extract information from this. All right, so how do we do this? Well, there are actually several ways to do this, but we would like to get optimal analysis. All right, so how do we do this? One is to do the brute force Monte Carlo Markov chain sampling of initial conditions. This is an extremely expensive thing to do, but I'll mention at the end that we're actually making progress on this as well. But here, let's focus more on the traditional AI approaches, which is, well, you make a lot of simulations of the data, you vary these cosmological parameters, and then you feed these to something like CNN or something like that to get the posteriors of cosmological parameters given the data. So this would be a typical discriminative approach, all right? We call this P of y given x. X is the data, y are the parameters. So this would be a classical discriminative approach. However, there's another way to do this, which is to learn the likelihood of data given the cosmological parameters. So these will be conditional likelihoods. And then you can use Bayes' theorem to invert this to get this. All right, so this has definitely some cons in the sense that the data, as I mentioned, are very high dimensional. We can, and so it's very difficult to train, but if we introduce some symmetries on the data, translational symmetry, but perhaps rotational symmetry, and perhaps multi-scale information, then we think we can handle it. And so our approach was to approach this with normalizing flows. Before I get to normalizing flows, let me just tell you how we create simulated data. So we use a method called embodied simulation. We start from some initial conditions in the universe, and then we just let gravity evolve in time. And so initially this is very nice and smooth and very Gaussian, and then as time evolves, we get more and more clumpy structure due to the nonlinear evolution of gravity. And then if our data are galaxies, then we have to make another step, which is we go from this, which is dark matter distribution, to something that's like galaxy distribution. All right, so these are kind of expensive simulations, but we have made a lot of progress over the years, how to make them faster, how to make them differentiable, and so on and so forth. I won't go into the details of that. So now imagine that we have this as the workhorse to get simulations. Then what do? Then we have to project these simulations along some distance, along the line of sight, basically between us and wherever the galaxy light is coming from. Okay, we call this ray tracing. We're literally tracing rays along the line of sight, and these rays are then being deflected, as I mentioned earlier, due to the fact that due to Einstein's gravitational effects, light is being deflected along the line of sight. This would be a few examples of that. And they're being deflected by these simulations, right? Which, for example, for nearby simulations, they would look like this. For more distant simulations, they would look like this. Okay, so that's how we, in the end, create maps. And then finally, we have to also put in realism of an actual telescope survey. And this is how a typical map would look like of the data. You'd see a lot of holes. These are holes from the fact that they're bright stars that you just can't really do anything about it, so you just throw the information around the bright stars away. You see, you have a lot of holes. And then other realistic effects come into the fact, well, you can't observe all the time, and things like that. So this would be a typical example of realistic data with all of the complications that you need. All right, so now imagine that we do this many, many times. We have thousands of these kind of realizations. But now we also need to vary the cosmological parameters, right? So we have thousands of these realizations of x, where I'm calling x data. But now we also need to repeat this as a function of y. And typically, we would vary 2 or 3 parameters in terms of y. That would be, for example, amplitude fluctuations and matter density, the 2 parameters I mentioned earlier. But then on top of that, there's also a lot of other parameters we need to marginalize over that have to do with astrophysics. Okay, I won't go into details of that, but just to give you the sense that this would typically be 6 or 7 or 8 dimensional parameterizations of the data. All right, so that's how we have the training data. We have literally 100,000 maps of order. Now we train with the normalizing flows to learn these probabilities of P of x given y. Normalizing flows, what are they? They are mappings from a simple distribution, like a Gaussian, to a complicated distribution, like something more complicated. And at each step, the map transformation is relatively simple. Why it has to be simple? Well, because we have to be able to do 2 things. We have to do the inverse of this transformation, and we have to also do the Jacobian, the determinant of it. So that's why they have to be simple, so that we can actually do these things. But if you concatenate a lot of these transformations, you can go from something simple to something complicated. All right, that's the basic idea. The training is based on maximizing the density. But the question is, how do we design normalizing flows for these kind of specific physics applications or cosmology applications? As I said, for normalizing flows, they have to be easily invertible and they have to be easily evaluating the Jacobian. But for physics applications, we also have to have other properties such as spatial structure modeling, maybe with coarse graining, translational symmetries, perhaps rotational symmetries, and finally, ability to learn efficiently from very stochastic data. Okay, so we have a couple of these normalizing flows for these applications, but I'll talk about this one here, which is we call multiscale flow, which is our most recent analysis. The idea here is that we are coarse graining basically a map. Let's say we start with 256 square map. We're first coarse graining into 128 square and the 3 differences, right? So we haven't lost any information here yet. But the way we then write down this density is the density of this map plus, well, in terms of log, plus these 3 maps, which are now conditional, right? These 3 conditional on this one, right? Now that we have this, we just keep doing this, keep splitting. For example, we take 128, and we again split it into 64, and then the 3 additional maps. So we haven't lost any information, right? Everything is bijective because we still keep the same number of parameters in the map, same dimensionality of the data. But these 3, again, are the conditional on this one. And so we keep doing this. So this is how we try to reduce, basically, the curse of dimensionality, right, by using the fact that these are strongly correlated spatial structures that have correlations on all scales. All right, so in terms of training objective, we actually start with a purely generative training objective, so maximizing this likelihood here. But later, we also add some discriminative objective in terms of the posterior. And this actually helps us then to get very reliable posteriors at the end. Because training just on the likelihood typically does not end up with the reliable posteriors, but that's why we have this mixed objective here. All right, as I mentioned, the one task we like to have with this is just to have faster simulations. Remember, I told you these n-body simulations are very expensive, so to create one map is very expensive. And here we have now a generative model that we can draw new simulations from it. And so here, again, the way it works, right? We generate first a coarse-grained map, then we generate the 3 additional differences that then allow us to upscale to 128 square, and then we just keep going. And we went all the way to 512 square, right? So in other words, 250,000 pixels. In terms of how well these maps compare to the original training data, here's a comparison. in terms of the power spectrum, in terms of one-point distribution function, we get perfect match. So we think these are, reasonably realistic representations of the underlying simulations that they were trained on. But again, I want to emphasize how stochastic these different data realizations are, right? Each data realization is completely different from each other. All right, so that's one task. The second task that, in some sense we care most about is doing the posterior inference and trying to learn basically the posteriors of the cosmological parameters given the data. So there are a couple of things that we're interested in that situation, right? One is that we want to have reliable posteriors, and the other one is that we want to have the smallest possible posteriors. In other words, smallest possible errors. Here I have a standard frequentist test. Even though this is a Bayesian analysis, right? We get Bayesian posterior contours. We can ask the question, well, are these reliable posterior contours in the sense, do they, is a 68% contour capturing 68% of frequentist in frequentist sense, and same for 95%. This is the standard empirical coverage, and we satisfy this very well. And so we're certainly doing a very good job in terms of quantifying uncertainty with this kind of approach. I'll show you in a few slides how well we're doing compared to the baselines. But before I get to that, right, so again, I want to emphasize that we are learning P of x given y, but Bayes' theorem is, we can just do P of x given y times P of y divided by P of x, and we get the posterior here. Okay, so that's how we get the posteriors. Okay, so, but the third task is really the trustworthy AI, right? Do we have, how can we be sure that we have covered all the details that are in the real data? And this is very hard because, you can't really ask this question directly. All you can do is you can try several different things to see if there's any anomaly popping up. We have two approaches to go after this. One is, are different scales consistent with each other? Because remember, this is a multi-scale flow, and we can do the likelihood analysis as a function of scale. And that's what we have done here. And when everything is good, these are all no simulations, not on real data yet. When everything is good, all of these posterior contours are consistent with each other. On the other hand, if we, for example, have a wrong, astrophysical model or wrong noise, then this is what we would get, right? We would get that these posteriors at different scales are very inconsistent with each other, and that is a red flag telling you that something is missing, that we have some lack of understanding of something. So that's one way to do it. Another way to do it is actually to use the actual density itself. That's the great advantage of generative models, well, at least normalizing flow-based generative models. They have the density estimation, and you can actually ask, is the density estimation that you get from the real data consistent with the density estimation numbers that are in the training data sets? If the answer is no, for example, if the density estimation from the real data is much lower, that is also an indication that maybe there's something missing in the real, in the simulations compared to the real data. Okay, and so here we're showing, okay, here I'm showing as this ROC curve, in terms of false positive rate versus true positive rate. But basically, the basic idea here is if the results are long diagonal, then you're not gaining anything. If the results are like this, then this density is actually telling you something useful about the anomalies. All right, here we injected some anomaly, and we asked the question, can we identify this anomaly by using the density? And because, from the fact that some curves look like this, the answer is yes, we can identify some anomalies by looking at this. And in fact, we can do this again as a function of scale. And so here we injected noise. Noise doesn't affect large scales, and that's why on large scales we have no effect, but then on small scales we get a pretty large effect. Okay, so we have two ways to identify unknown unknowns, and that's a good thing, right? Because that is basically a goodness of fit test that has been in some sense lacking in a lot of these AI applications, right? You get some results out of AI, but you have no idea how reliable they are. Well, here with generative approaches, especially with the density estimation, at least you may have some hope that you may be able to identify some of these issues. All right, finally, how well are we doing? It turns out that these methods are extracting a lot more information compared to the standard baselines. So here I'm showing you basically the posterior contours. Green is the baseline analysis using the power spectrum, And this red is our analysis from multi-scale flow. And the errors are, you can see errors are much, much smaller in this analysis compared to the power spectrum. So there's really, tremendous promise in terms of applying these AI methods to the cosmological analysis and extract much better information. And of course, if you extract much better information, you have much better hope to find something new and perhaps find some new major discovery. All right, so that's always the promise, right? That there will be there's still something in our understanding of cosmology and the universe that we are missing, and then maybe analysis like this will discover that. And if so, if there is still something to be discovered, then AI tools, clearly can have a big impact in terms of discovering this thing much faster, much better. All right, so that's the excitement message. The exciting message that I want to leave you with on this subject. Let me now switch gears to my second part, which is physics for AI, and discuss this new sampling method that we developed. All right, so first question is, can physics ideas influence AI? The answer is yes. Well, Nobel Prize this year has been given for that. But diffusion models, for example, have been also, are based on physics ideas. So there's a lot of, interplay between physics and AI. The area I want to focus on is Monte Carlo macrochain sampling, where the idea is you want to sample some target distribution, but you don't know where that target distribution peaks. You don't really know. You want to find it. You need to find it. So this is very similar to optimization, but slightly more complicated. And I'll actually discuss in a few slides what the differences are between optimization and sampling. Okay, but what is sampling idea? Suppose you have a target density distribution that looks like this. All right. You want to find samples that reproduce this density distribution. Here is a typical Hamiltonian Monte Carlo output. Trajectory and how it puts down the points. And here would be a typical, for example, Metropolis Hastings, which hasn't converged yet, right? But you see, basically, this is more like a random walk, and so it's very slow to move around. Anyway, over the years, there has been a lot of methods that have been discussed. As I said, Metropolis it was the first one, the famous Metropolis algorithm. These days, if you have gradient access, which we do with machine learning tools such as automatic differentiation, then the two most popular methods are Langevin Monte Carlo and Hamiltonian Monte Carlo, and they're very closely related. Okay, so let me tell you a little bit about Hamiltonian Monte Carlo. The idea of Hamiltonian Monte Carlo is that you upscale the dimensionality, so you don't have just these x positions of the parameters, the values of the parameters, but you also have their momentum. Okay, so you create basically a dynamical model, and then you use Hamiltonian equations to trace this Hamiltonian system of equations, where the potential in this Hamiltonian system is simply given by the log of the target density. Okay, and this is something you can evaluate at every point. And this thing will be going around. This is in phase space, x and pi, momentum, position. Will be going around, but then you have to resample every now and then. And once, if you've done this many times, you project it, you get the target distribution. So, but you have to do this resampling. All right. So our idea was, well, can we actually create something where we have a constant energy, and so we don't resample the momentum, and our distribution actually, in terms of more general distribution, is not canonical, so it's not e to the minus Hamiltonian, but it's a delta function, so it's a microcanonical distribution. Those of you who are familiar maybe with Boltzmann machines, you're probably familiar with this thing. Again, Nobel Prize was given this year for this kind of stuff. But you can also do this with microcanonical distributions where you have a delta function in energy. And then the question is, well, is there a Hamiltonian equation that will, as you project this, you sample this thing and then you project, is there a Hamiltonian equation that gives you the target distribution? And the answer is yes. It turns out that instead of, for kinetic energy, instead of being usual velocity square, it has to be log of velocity square. All right, this is the actual Hamiltonian that you need to sample. Okay, so that's the basic idea. I want to show you this. Okay, so this is a simulation of Hamiltonian Monte Carlo. You see it's going slow at the edges and fast to the center. if you take then samples of this thing, of these dynamics, it will not actually give you the right distribution. It will actually give you a lot more samples here than in the tails than in the high density. Okay, so however, and so this is why you need to resample the momentum. On the other hand, MicroCanonical one, you see, is just the opposite, right? This one is actually very fast in the low densities because you don't want to spend a lot of time in the low density, and it's very slow in the high density regions, as it should be, right? So this one actually has the potential of actually giving you a correct sampling distribution, even without resampling the momentum. All right, so okay, and there's, so far I was talking about Hamiltonian, microeconomic Hamiltonian version. There's a version of doing Langevin, this where instead of resampling the momentum, you just slowly add noise to it, and this, we call this microeconomic Langevin Monte Carlo. And this one is typically a factor of 2 faster than the other one. All right, are these methods better than Hamiltonian Monte Carlo? The answer is very often yes. Here I'm showing, for example, a Cauchy distribution, which has a very fat tails. This is, I forget, something like, I forget what's the dimensionality, but I mean, something like 50-dimensional problem. At the same number of calls, gradient calls, this is how big the bias is. But let's just look at this plot here. We had a million calls, and MC-LMC got us a perfect distribution. So the analytic solution is this blue line, and our distribution, the blue points are, the histogram is essentially perfect. Whereas Hamiltonian Monte Carlo, you see it's very noisy and it's really not sampling the tails very well. Okay, now this thing is also a very fast optimizer. This is what Hamiltonian Monte Carlo is doing on its own, and you see it's basically, it falls into the target and it just does something there. And then if you resample momentum, then you will slowly get towards the target, but it will be very slow. Microcanonical version of this is a very good optimizer. So it does this trajectory and then it goes straight down. All right, so it looks like this. And you can see that, therefore, in terms of optimization, is a lot faster. Okay, and that I think is important in terms of what kind of performance it leads to. So I think this has significant advantages in terms of just burn-in time of the samplers, but also potentially for optimization. All right, so let me talk a little bit about this optimization versus sampling, because the two tasks are very similar. And we know in machine learning, we typically just do optimization. We don't really do sampling. However, there are situations where you need to sample rather than optimize. And this situation is when you try to determine some hierarchical parameters. For example, the hyperparameters of neural networks and things like that. A very typical example would be, for example, weight decay constant. If you just want to determine weight decay constant as part of your optimization, you will completely fail. You'll just get the answer is 0. And there are other examples here with, for example, we have an example of Brownian motion, hierarchical example. We have 5 different starting points and atom trajectories. They all end up somewhere here. Okay, now the true answer is here. If you do sampling, sampling will always take you in the region where you have the correct value. All right, so this is just a message that in some examples, sampling has a significant advantage, but of course the problem is that it's more expensive. However, this method that I just described, a microcanonical method, actually is also a very efficient optimizer, if you want, in the sense that it gets into a typical set very quickly, and so that's why it may have some advantages over the optimization, even in the machine learning context. All right, so recently we developed an ensemble version of this method, and again, the motivation here, typically MCMC sample is very expensive, but we have GPUs. GPUs can run thousands of these processes in parallel. So why don't we run thousands of these processes in parallel and use the information to determine step size and things like that. And this can lead to really major improvements in terms of wall clock time. And here I'm showing the results compared to the standard baselines in terms of ensemble Hamiltonian Monte Carlo. These are nuts, cheese, and meat. These are all from the same group at Google. And this is how many likelihood calls we need in order to get very small bias on the final answer. For example, for a banana example, which is not a trivial example, we just need 18 calls and we are done. Some other processes, of course, need a lot more, but observe how much better we're doing. For example, I don't know, on ill-conditioned Gaussian, we're doing about a factor of 20 better than alternatives and so on. So this can be massive improvements compared to the current baselines. And again, this all goes in this direction, right? Well, maybe if sampling can be as fast as optimization, maybe this is better to do. Okay, so I believe that future of sampling is, doing ensemble sampling on GPUs, and I'm certainly excited about this particular application, and we'll be releasing this code very soon. We have recently ran this for Bayesian neural networks, which one can argue are pros and cons of Bayesian neural networks. Usually, the main con of Bayesian neural networks is that they're very slow. Nevertheless, people have shown that if you do deep ensemble, some kind of ensembling version of rather than just take results of a single optimization, maybe have different initial conditions and then average those results, that is better than a single in terms of performance. But people have also shown that Bayesian deep ensembles are better than deep ensembles, but they're slow. Okay, so what we have done here is we have used this MicroCanonical version to do basically Bayesian deep ensembles. And in terms of RMSE and log posterior probability density, we get state-of-the-art numbers compared to the deep ensembles. For example, you can see basically, these are all regression tasks. You can see, in some cases, the improvements are massive, right? A factor of 3 better. And these are, again, deep ensembles. And we already know that deep ensembles are better in terms of this performance than just a single run. So these can actually be massive improvements in terms of performance. But the problem was that Bayesian deep ensembles are, using Hamiltonian Monte Carlo, they were a lot slower. You see, there's factor of 10. Higher computational cost, which is why people don't often deploy them. But we have now reduced these computational costs to be roughly the same as deep ensembles. So in other words, we achieve performance of Bayesian neural networks while at the same time achieving the runtime costs of deep ensembles. So again, this is something that may be worth looking more general. Basically, can we achieve and can we make sampling with mini batches as fast as optimization? If that would be, I think, an exciting direction to look into because as I try to argue, there certainly are some parameters where sampling really gets you to the right answer where optimization does not. Okay, so finally, now we are doing a full circle, and we went from physics to AI, but now we are going back to physics and deploying these methods, these sampling methods, to many different physics problems in my field, for example. We're doing cosmological inference, we're doing statistical physics, quantum lattice models, and we're looking into whether these methods can be used for things like molecular dynamics and so on. Okay, so this is basically, again, a statement that the methods that, have been developed for, the methods that have been developed, the AI methods maybe have been inspired by physicists, right, and developed and then AI was developed, but now they are coming back and actually advancing physics itself. All right, so I'm at the end of my talk, so I want to, let me just restate my main conclusions. AI, in terms of AI for physics, AI can be used for a lot of the tasks that we want to have in scientific data analysis, for example, data generation or simulations, data analysis, and anomaly detection. And for many of these physics applications, it's actually better to combine generative and discriminative architectures and loss functions so that one has the best of both worlds. In terms of AI for cosmology specifically, I am very optimistic that we will actually be able to improve over the standard baselines by a factor of several. And that is huge, right? When you have billions of dollars investments into these telescopes, if you do 10 times better, that's literally like, instead of getting 10 billion investment for 1 billion, something like that, right? So this can be really, really major improvements. Finally, on physics for AI, I was trying to show you how physics inspired dynamics, new dynamics equations, and new approaches to the distributions, such as microcanonical distributions, can actually lead potentially to better sampling, which in principle it has nothing to do with physics, right? But the methods that are inspired by physics can actually be applied to sampling and potentially even to problems such as optimization and so on and so forth. Okay, so I'm particularly intrigued whether some of these sampling methods can be competitive against optimization and perhaps even outperform them, given this inspired by this physics dynamics that seem to be working really, really well on these applications that I've shown. Okay, with that, I'll stop here. Thanks.
Thank you very much. Thank you very much, Professor, for that thorough and interesting presentation. So he talked about physics and artificial intelligence, how these two different concepts can mutually benefit one another. Now we will get questions from the floor. If you have any questions, please let us know. Please raise your hand. I guess there is no question. Then, oh, there.
Hello, very nice talk. You mentioned the applications in lattice QCD, which I think is very interesting. So can you say in which direction you're thinking?
Yes, so I removed those slides from my talk, but on 5 to the 4 model, which is the simplest continuous version of Ising spin model, we have at least an order of magnitude improvements compared to the Hamiltonian Monte Carlo. And if you scale these up to high dimensions, then it would be 2 or 3 orders of magnitude. And so now what we're looking at is, and talking to the lattice QCD people, is whether they should adopt these samplers for their state-of-the-art lattice QCD applications. Right? So that would be one example, because those are very high dimensional.
Just another one. Would you have biases also in this sampling? Do you need to debias because there's sometimes a...
Right. So we actually are developing a method which has Monte Carlo adjustment. And that's a very good question. It's very interesting how different fields have different standards. For example, lattice QCD people insist on unbiased method with metropolis adjustment, whereas molecular dynamics people don't care at all, right? So, and it's very interesting how these different cultures have been developed, and not always for very rational reasons, right? And so it's, in any case, the bottom line is we have a metropolis adjusted method now that, and so that's also something we are almost about to publish. Yeah.
Thank you. All right, is there any other question? If you are too shy to ask questions, then Professor will be here until the very end of this conference, so you can maybe visit him and ask him a question. All right, once again, thank you very much, Professor Seljak, and let's give him a big round of applause. Thank you very much.